Good morning, good afternoon, good day to everyone who's tuning in for the first in CNL's low-dose radiation webinar series. Just a few very brief housekeeping notes for those that may be unfamiliar with the platform. This broadcast is being delivered through Teams live event. This allows us to send the broadcast to a large number of people all around the world. However, the downside is that we're not able to talk with the audience. However, we would welcome questions and we can take them up towards the end of the session. If you'd like to submit a question at any point, and I would encourage you to submit them when the question strikes you, you'll use that with the Q&A button. It should look like a small speech bubble with a question mark in it. If you click on that Q&A, you're welcome to send your question in and we will take them up at the end of the session. Today's webinar should run about an hour, so that'll be about 50 minutes of presentation and then some time for Q&A at the end. And so with those remarks out of the way, I would now turn things over to Dr. Edward Azam to kick things off. Edward?
Thank you, Philip, and warm greetings to everyone from Chalk River, Canada. It is really a distinct honor to introduce the first speaker of the Canadian Nuclear Labs webinar series on the biological and health effects of exposure to low-dose ionizing radiation. Our speaker, Antone Brooks, or Tony Brooks, as many of us call him, has had a distinguished career not only in studying the biological effects of radiation, but also in promoting research in the field as an administrator and in guiding numerous scholars in training. I am indeed one who was fortunate to be guided by Tony in my career. As a native of southwestern Utah, Tony has had a front row view of the nuclear tests conducted at the Nevada test site. At the onset of his undergraduate studies at the University of Utah, some 20 years into the atomic age, he went on to chase radioactive fallout. This interest grew further during his master's studies, where he focused at the transfer of iodine-131 and cesium-137 to cow's milk and the subsequent uptake by local residents. Tony pursued doctoral work at Cornell, where he examined gamma-ray effects on chromosome changes in testes and bone marrow of Chinese hamsters. Upon defending his thesis work, he was fast recruited to work on chromosomal effects of internally deposited radionuclides at Loveless in New Mexico. In 1989, he went on to study the effects of radon at Pacific Northwest in Richland, Washington. However, I believe that a highlight of his career was as chief scientist of the low-dose radiation research program of the US DOE. The many projects in that program have really led to paradigm shifts in our thinking about radiation effects. Notably, they have shown that biological responses at low doses are unique and can be unrelated to what occurs at high dose exposures. Tony has had an illustrious career of service to numerous agencies, with over 30 years serving the NCRP. He is a recipient of numerous awards, including the 36th Lauriston Taylor Award of the National Council on Radiation Measurements and Protection. Today, Tony will talk to us about his journey in the radiation sciences, the past and present, and lead us into a look to the future. Tony, welcome, and thank you very much for giving this first webinar.
Tony, you're just on mute there. Just unmute your microphone.
Can you hear me now?
Yep, sounds good.
I've always enjoyed working with the Canadians. Between Ed and Doug Borum and so on, we've had an awful good relationship. In the DOE low-dose program, we decided that we would fund anyone throughout the world who had a unique technique or unique experimental design, as opposed to just funding the United States people. So we got into Canada very early. Next slide. Nuclear weapons were really a part of my early life. Those mountains in the background, I'm just right on the other side of those where I was grown. Next slide. This is my hometown, St. George, Utah. We'd be up early in the morning and the sky would light up above the D. And then we could count and feel the earth shake. And by doing that, we could calculate how far out on Yucca Flats or Jackass Flats the weapon was sawed off. I was a kid, that was really fun stuff. Next. So we shot over 100 atomic bombs above ground in Nevada. The fallout patterns, they'd shoot them so they'd go north across Nevada, across the Nevada desert, and then they would turn east across Utah. I lived in St. George there, and most of the time they missed St. George, but they had one cloud they called Dirty Harry that went the wrong way, got to St. George very quickly. And so they had a little truck that would drive around and say, hey, go in your house. There's a fallout cloud coming over. So that was about all that happened. Next slide. So I chased fallout. We had a whole series of test stations around the state. And this just shows the cesium in those stations and the above ground nuclear tests that were shot right in here. So you can see that some of that came before the above ground. So a lot of this may have been actually worldwide fallout. Next slide. So we rounded up a whole lot of people and put them in the counters and recounted them. I thought, well, I better get in and see what I've got. So I'm here, ALB here on the end. You can see that I had one of the highest cesium burdens of anyone. So I was worried. Are we going to have cancer? Is my family and my whole area going to be plagued with cancer? So that's what I decided I would study. Next slide. So here's the Nevada test site fallout pattern. Next slide. The worldwide test fallout pattern. Next slide. And here is the cancer mortality rate. So what I'd like to point out is in Utah, right there's where we lived. Utah has the lowest cancer rate in the nation. Washington County or southern Utah, where I was, where the fallout was, had the third lowest cancer fallout pattern in the state. Now, what the world's going on as you look down the Mississippi River there? Whew. I always like when I'm talking live to kids or students or what's going on in Mississippi. Cause that. I just said, well, everyone in Chicago pees in the Mississippi, so that's what that is. Next slide. So radiation-induced cancer and genetic effect, when I started studying, they thought that they were about equal. That the risk for genetic effects and radiation was about the same. The Hiroshima Nagasaki data was the biggest data set we have. And they decided that between about 0.5 and 3 sieverts, 5% increase in cancer per sievert. So if you take environmental levels down in the millisievert range, you can calculate the increase for a millisievert. Ooh, almost nothing. Are the risks for genetic damage equal to cancer? So in the early studies, we started studying that. Oak Ridge had a big study on genetic effects. And the other thing was, what about genetic load? Each one of us carry a lot of bad genes. Hopefully we marry well and our spouse covers those bad genes so our kids turn out decent. I think that was the case for me. Anyway, next slide. So this is the megamount study that Bill Russell and his wife conducted. Radiate the males with a fairly large dose, 3 gray plus 3 gray, not quite lethal, but a lot. Made them with homozygous females, and then they would count the mutations. So 100,000, 120,000 mice, 100 of them had mutations. Very, very low frequency. Next slide. Now, does radiation exposure increase the genetic load? In other words, if we get radiated, do we have more and more and more abnormal genes in the gene pool? So Jake Spalding of Los Alamos did a multi-generation mouse study where every generation he would radiate the males, cross them, did that for 20 generations. After radiation, 20 generations, couldn't see any change in sex ratio, litter size, any indication of change in genetic load. So genetics then, as we started writing up the beer reports, kind of fell out. The main risk then from radiation remains as cancer. Next slide. So what I was worried about, well, that's all right for external exposure, but what about internally deposited radioactive material? That's what I had. Cesium, iodine, plutonium. There was plutonium that did not ignite during the bomb, so it was scattered around. So I went to Lovelace, and that's what we started doing, was studying the risk for strontium, radium dial painters, iodine, plutonium. At one time, the quote was, plutonium-239 is the most hazardous substance known to man. A single hot particle of plutonium in the lung is going to cause cancer. So that's what I tried to do, is find a question that I had great interest in and then research it. So any of you young researchers, that's what I'd try to do. I'd find a question that you're really interested in, something that really drives home to you, then follow it. Next slide. So this is the work that Otto Robbie did down at California, where he fed dogs strontium-90, mothers all the way through their life. And you can see that it takes a lot of radiation, a high dose rate grays per day over a long, long period of time before there's any increase in bone cancer. Next slide. The radium dial painters, of course, had young ladies that were licking the brushes and painting. They got some huge doses of radiation. You can see that out to about 1,000 centigrade, there was no increase in bone cancer. But at the higher doses where you have tissue disorganization, you have inflammatory responses, then you get cancer. Because of these studies, then bone was found to be very radiation resistant. Next slide. So then what about iodine? Iodine 131. We could do iodine function tests on people in Utah because of the fallout. Iodine 131 in the fallout has an 8-day half-life. What about iodine 129? We've got it out here in the Hanford Waste. Lots of it. Has a 10 to the 7th year half-life, so it's going to be there a long time. Oh, we better worry about iodine 129. But it requires so much more mass of 129 than it does 131 that it's really not a problem because you can't get it into your body. The guy named Book there at the University of California, Davis, fed dogs and mice and rats iodine 129 straight, could not get enough into the thyroid to do anything. The last thing, iodine 131 gives off a bunch more radiation per unit time as the same mass of 129. 1 microgram of iodine will give the same dose as a kilogram of 129. Now, you're not going to get a kilogram of 129 into your thyroid. 129 is not a radiation hazard, but we spend lots and lots of money trying to protect against 129. Next slide. So, no increase in thyroid cancer in all of the medical fallout nuclear accidents. There was an increase in thyroid following Chernobyl. There were some huge doses to the children in Chernobyl, and there was an estimated 7,000 excess cancers. When they followed up all those kids, they had less than 10 deaths from those cases. Again, the thyroid is probably where you want to get a cancer if you can get one, because you can lop it out. So there's really no potential risk from thyroid cancer from 129 iodine. Next slide. Is plutonium the most hazardous substance? Is the hot particle hypothesis true? This is another question that came up while I was working, and so that's one of the questions I wanted to address. Next slide. So I was studying chromosome aberrations in the liver. One nice thing about the liver is that the alpha, a lot of the radioactive materials go and concentrate in the liver. They sit there daily radiating. So we did 3 alpha emitters. One in California had fission fragments, acute and chronic cobalt, and 144 cerium, beta gamma. And we found that all of the alpha emitters were almost 20 times as effective in producing chromosome aberrations as chronic beta exposure. And I think in some ways the factor of 20 that comes into estimating the risk of alphas versus beta gammas came partly from these kinds of studies. Now, when we went to doing cancer from them, the alphas were only about 6 to 10 times as effective. So that should be the real number that should be used rather than 20. Next slide. Now, what if a single plutonium particle deposited in the lung can cause cancer? This was the hot particle hypothesis. And if that were the case, nuclear power would be absolutely unacceptable. Next slide. The hot particle hypothesis. Okay, this shows a picture of a lung with some alpha particles deposited in it. You can see the little stars there. The lung cells next to those stars are really getting the heck kicked out of them. The rest of the lung is not getting any radiation dose. So non-uniform dose of inhaled plutonium was a big concern. So I went to my aerosol scientist there at Loveless, Otto Robbie, and says, Otto, I want you to give me a bucket full of very large particles, medium-sized particles, and small particles. He says, Brooks, you act like you're ordering a loaf of bread. That's a hard problem. I says, I know, but you're smart. You'll be able to do it. And they did. They invented a particle separator, like an old cream separator, put it in a centrifuge, big particles here, cut it out, the foil that they put there, and you could get known particle sizes. So I had a pot of each particle size. So I said, well, I'll inject those into animals and see what happens. Next slide. So this just shows plutonium citrate. You can see some of the little individual tracks. Each and every cell was uniformly 0.3 microns, 0.8 micron particles. Very few of these 0.8, but boy, you can see that the liver cells around those particles are really getting hit. Now, is that more hazardous than the citrate? And that was the question that we were trying to ask and address with these studies. Next slide. My goodness, when I saw these data, I could hardly believe it. The chromosome aberration frequency per cell was the same regardless of the particle size. The liver was responding as a whole unit, not as individual cells. Up here, woo, nice linear dose response, not dependent on particle size. Next slide. So when we looked at the cancers induced, Citrate was most effective. All the particles were about the same, much less effective in producing cancer in the liver. So in my mind, next slide, the results of the research, hot particle process is not supported. Next. To get cancer, you hit as many cells as you can. Next. Uniform distribution is more effective than any other particle. So, to me, the hot particle hypothesis was dead. Next slide. Now, what about radon? I went up to Pacific Northwest Lab then from Loveless. They were doing a lot of radon studies. Radon is responsible for more than half of our total radiation. Uranium miners were developing a high frequency of lung cancer. Next slide. What if radon is killing us in our homes? They set up a huge, EPA set up a huge program to try to monitor homes for radon. Next slide. Now this is, I was on the Beer 6 committee, which was a committee designed to study the health effects of radon. And we put out the Beer 6 report, which I thought was a good report, very scientific. But then somebody, not me and not some of the other people on the committee, wrote the bottom line. And the bottom line that they said was, radon is the second leading cause of lung cancer next to cigarette smoking. So I took one of the tables, 3-10 in Beer 6, and made a graph out of it. So if you don't smoke, your radon increase is way down there, almost non-existent. Very hard to find lung cancer among non-smoking uranium miners. However, if you smoke, lung cancer death goes way up. Then if you're a uranium miner and smoke, there's a significant increase in lung cancers among uranium miners who smoke. I remember talking to Gino Saccomanno, who was down in Colorado doing the early uranium. He says, you know, I don't remember ever seeing a lung cancer in a non-smoking uranium miner. Of course, there are some, so that's where we get this number. Whew. So, next slide. So radon alone is not second or third or fourth or 10th cause of lung cancer as long as you don't smoke. Radon interacting with cigarette smoking may be the second leading. So if you have radon in your homes, don't smoke. Next slide. So next we decided Senator Pete Domenici of New Mexico got the money for a low-dose radiation research program. It's a picture of Senator Domenici. Since I was working in New Mexico, we had quite a lot of interaction with him. Dr. McClellan, my boss, spent a lot of time with the senator. In this year's Energy and Water Act, we initiated a 10-year program, $13 million a year, to understand how radiation affects genomes and cells, so they can really understand how radiation affects living organisms. This was his dream. For the first time, we will develop radiation protection standards that are based on actual risk. The program lasted just over 12 years. We were funding it about 20 million by the time it was over. I was actually given the job as chief scientist on this program. I told my wife, if I could have designed a job for me, the last part of my career, I could not have designed a better job. I thoroughly enjoyed this. It was a wonderful, wonderful time to be involved in the research. I got to meet all the scientists. I got to take some of the scientific writing that the public doesn't understand and put it in terms that the public could understand. Next slide. So we kind of made this little Venn diagram to show that low dose responses are very different than high dose responses. And we had three very distinct new paradigms for low dose radiation. There was one, we call them the adaptive response, genomic instability, and bystander effect. All of these are infected by the genetic sensitivity of the system that you're using, whether it's cells, animals, or people. So what I'll do quickly is run through each of these with you, starting with the adaptive response. Next slide. Next, next, and next. This is Shelley Wolf's work. He has the controls. He gives them 0.5 rads per centigrade, or he gives them 150, observed and expected the same. However, if he gave a small, what he called tickle dose of 0.5 plus the 150, the observed was way less than the expected. So we call this an adaptive response. And this was one of the main endpoints, or one of the most important endpoints that we had in the DOE low dose program, where people were using different kinds of radiation, different biological systems, and trying to look at adaptive response. In fact, I think Ed did some of this work also, he and his wife both. Next slide. So, transformation frequency, Dr. Redpath down in California. Oh, at low doses, there's a protective effect. It goes down. It's not linear. Next slide. So there are a whole lot of different systems that show the same response, a decrease in frequency of the endpoint as a function of low doses of radiation, rather than a linear dose response. Next, genomic instability. Now, genomic instability is if you radiate the cells, they seem to be normal, they go through quite a few cell divisions, and then all kinds of abnormalities start popping up. This is Bob Ulrich and Brannon, who did this genomic instability in mice. Had a sensitive strain of mice, the BALB-C, and a resistant strain, C57 blacks. And you can see that you radiate them, the number of aberrations per cell increases. In the sensitive strain, it goes down, and then whoo, after several cell population doublings, and these aren't generation doublings, these are cell population doublings, the frequency of aberrations goes way back up in the sensitive strain. And this then was related to the frequency of cancers that are developed in the BALB-C versus the C57 blacks. So genomic instability was quite a concern. Lots and lots of research on it. Couldn't see any evidence of it in A-bomb survivors, couldn't see any evidence of it in many, many cell systems. So to me, genomic instability was not as big a concern. Next slide. And we also found that genomic instability could be modified by a pre-exposing adaptive response. So if you have your controls, you give them a low dose, 1, 2, 3, or 10 rads or centigrade. You give them 1, 2, 3, or 10 rads of centigrade and 500, whoo-hoo. No difference. 500 by itself, lots and lots of colonies. So it showed that low doses can actually protect against genomic instability. Next slide. Now, bystander effect. This was made possible because we were able to develop, there at CNL where I was working, Les Bravey developed a single cell shooter where he could shoot any cell he wanted to with any number of alpha particles. We also had people develop shooters that would use gamma rays. So with these, you knew exactly which cell got hit. And so I would go in and score the chromosome damage in the hit cells, the non-hit cells. Wonderful tool. Next slide. This just shows some of the gamma H2AX responses to some of these cells. You hit them with a single 3 MeV helium atom or alpha particle. You can see the little gamma H2X dots, focused X-rays. When we first did this, I told Les Braby, who was running the machine, boy, it would sure be nice if we could write DOE in one of those cells with his radiator, but no, he didn't have that kind of resolution. He could hit the cell, but he couldn't write with it. Anyway, it showed that individual cells, you know which ones are hit. You can actually then go in and score the hit cells versus the non-hit cells. These are the results in the next slide. There were micronuclei and non-exposed cells. He was radiating the pink cells. The blue cells were not irradiated. Oh, micronuclei right there in those blue cells. This was stuff that Charles Gear did there at Columbia University. And the next slide shows some dose response from these kinds of studies. Next slide. It went up and then plateaued off. Number of particles per targeted cell. So it was showing that a bystander effect was not the same as the cells being hit. It went up and then plateaued off. Anyway, with those, that was kind of what we had done at that time. Next slide. The other thing that we had was that Andy Wyrobic did some gene expression studies, and he found that if you, this is dose across here, and these are kind of neat. You see the blue up in this corner moves as you increase the dose down to the blue in this corner, the red moves. So these are the nearest neighbor analysis to try to see which genes are turned on by different doses of radiation. The low dose genes obviously are very different than the high dose genes. These were very early studies, and lots of work have been done now on gene expression as a function of radiation dose. And the genes turned on by low dose are very different than the genes turned on by high dose. In fact, I remember Doug Borum once saying that the genes turned on by low dose are a lot like the same genes that are turned on by exercise. So anyway, that's where we were to. Next slide. Randy Jerdal and I have known each other for a long time. Randy's a radiation biologist. Randy had a mouse strain that he could feed these mice a different diet and change the looks of the offspring, change the phenotype. Normally, these are nice little brown, shiny mice, but if you feed their mothers a certain diet at a certain time during gestation, they turn out obese, yellow, cancer-prone, and diabetic. So he came to us at the low dose program and says, I'd like to do a dose response in the low dose region to see what radiation does to these epigenetic effects. Now, these are not genetic effects. These are epigenetic effects. Gene effects that do not change the base sequences. So yeah, we did that. And Randy and I were riding to the airport from one of our meetings together. His phone rings, he starts talking to Burnell, who was his student, young lady. He hangs up the phone and says, dang, brown, brown, brown. They're all brown. I says, what do you mean, Randy? Well, the radiation, instead of making them more obese and yellow and cancer prone, shifted them back to the normal phenotype. That was a protective effect. I thought, geez, Randy, that's a wonderful, wonderful result. Why are you saying dang, dang? Can you imagine the amount of money that would have been poured on Randy Journal's head if he would have shown, oh, here's an effect of radiation we didn't know about before. Epigenetic effects of radiation are really serious. We've got to really study this. But brown, they're all brown. Huh, who's going to fund that? So anyway, that's another of the problems that we have, is communicating the importance of some of these studies to risk. And this is about where we were too when the program was terminated. Next slide. PNL, where I was working, boy, they had all kinds of microwaves, proteomics, multiple power blocks, all kinds of things. And they would do these networks. And it was really exciting because there's certain networks that were turned on by low dose and others by high doses. Wonderful stuff. Don't expect any of you to understand all of that. That's my smoke 'em slide. Anyway, next slide. So the research results, extensive research on the biological effects. Some paradigm shifts. We couldn't keep thinking about radiation as a single hit. I remember as a kid when I was just starting to study radiation, they said, oh, radiation's like a gun. You set a television set up and you shoot it with a 30-06 rifle and hope to improve the resolution or the sound. Not going to happen. That's what we had, was hit theory. You hit them, you got to damage them. But now with bystander effect and tissue effects, hey, maybe a little radiation is very different than a lot. The linear dose response versus protective adaptation. Oh, low doses seem to be protective. Oh, mutation theory versus atomic instability. Radiation produces individual mutation. That mutation is passed on. That mutation results in cancer. Genomic instability, you radiate them. Lots of things happen. Then things start to happen. Well, you can modify the process. Next slide. So the mechanism of action need to be carefully documented. So that's where I think the future has to go. We've got to get back down into the mechanisms and understand what are the differences. High doses, low doses, this system, that system. And how do these relate to standards? Next slide. We've got another one on that one, I think. There we go. Low dose response are nonlinear, sublinear at all levels of biological organization. We've looked at the molecular, the cellular, the tissue, the organism, experimental animals, humans. Question. The science suggests that LNT overestimates risk in the low dose region where standards apply. So if we can actually show that in a way that can be accepted by the regulators and the public, then I think we could do an awful lot to relieve some of the fear that's generated. And one of the problems that we have is people, you say, oh, radiation, immediately, if I was radiated, I'm going to get cancer. If I get cancer, it was caused by the radiation. No. Radiation is not a very big hitter in the whole cancer process. Next slide. Another thing that we did with some of the Canadians was to go back and look at some of the old dog data for lung cancer. These animals inhaled a number of different radioactive materials. This is for yttrium-91, infused clay particles. The particles went to the lungs, they stayed in the lungs, and they radiated the lung. If you gave them too much, they died of lung pneumonitis and fibrosis and killed them. You cut back a bit, they survived that lung cancer. You cut back a bit more, the cancer frequency was not much different than the control frequency. So I thought that was really interesting, so we got some of the Canadian young people to help us with that. Went back and studied some of the dog studies. Go ahead, next slide. Whew. Got a couple of really nice papers out of this, where we related the dose to the number of cell turnovers. The lung cells are turning over all of the time. And we could see that if you give them too much, the red one, you kill them. Pulmonary interest, they die. The next levels, you get the lung cancer. But if you get the level low enough, it didn't matter whether it was strontium, cerium, yttrium 90, yttrium 91, no difference from the controls. So to me, that's really interesting because these lung cancers in the controls, they had doses that there were lots of mutations. There were lots of chromosome aberrations, but they didn't have inflammatory responses. They didn't have cell death. They didn't have tissue disorganization, all of which were involved when you had lung cancer. So I really appreciated being able to go back with some smart students. The smart students did the work and put together some of this stuff. So the influence of dose per cell cycle on lung cancer, high dose and low dose rate. So this is some of the kinds of things I think we can do. We've got a lot of other data out there that can be reworked. Next slide. So the dinosaur of linear no threshold hypothesis dead for low dose risk assessment and overestimates the risk. However, it remains used. Is it useful? So if we see down here, oh, we've got the dinosaur of LNT. We've got selective apoptosis where radiated cells die. We got bystander effects, we got ROS modification, we got adaptive protection. We were just starting to use genomics, proteomics, metabolomics, epigenomics to study these things. And that's when the program died. Next slide. Radiation is a poor mutagen and carcinogen. It really is. It takes a lot of radiation to cause cancer and to make mutations. In the low dose region, it may even be protective. Low dose and low dose radiation is very small, difficult or almost impossible to detect without huge studies. Now, John Boyce now has put together what he calls the Million Man Study, where he's generated huge databases. And the results of those studies are really very interesting. Early results show that there's no difference between men and women. Oh, we've always been assuming that women are more sensitive. Early results show that there's no increase in cancer frequency in the people who participated in the A-bomb test. I had a brother who was one of those in the trenches where they shot an A-bomb off right over the top of the troops. Afterwards, they said, oh, all clear, you can march towards the cloud. They did that to see if people would obey orders in a nuclear war. Not a very smart thing to do, but there was no increase in cancer in that group, according to John Boyce. Next slide. So the fear of radiation, whoops, go back, excuse me. The fear of low dose radiation is based on LNT. It kills people and is very expensive. Fukushima is the classic example. My friend Bruce Church and I wrote a paper comparing southern Utah to Fukushima. In southern Utah, we received about 3 times the radiation dose that they did in Fukushima. Southern Utah, they told us, go in the house, you're going to be all right. No increase in cancer, in fact, a very low frequency of cancer in our population, probably related to lifestyle. LDS people do not smoke cigarettes. Fukushima, They evacuated a whole lot of very sick people. They killed over 1,000 people in the evacuation because of using the LNT. So I think it's really important to understand when you do make a decision like that, you've got to consider everything, not just the radiation dose. There was no reason to evacuate all of those old people and kill so many of them. Next slide. So what are the costs of society because of the fear? Nuclear waste cleanup. Here at Hanford, this is where I live in the Tri-Cities, $2 to $4 billion a year to try to clean up to levels below natural background. Wow, it's really good for our economy. Boy, we have a humming economy here in the Tri-Cities, but we're not really cleaning up anything. We're just moving it from one place to another. That makes it so that we're doing environmental isolation. I think if we call this environmental isolation rather than waste cleanup, we'd be far more accurate. Nuclear power. Fear caused the delay in closing of many nuclear power when our need for power is increasing. If we're going to drive electric automobiles, we got to have electricity. We've dammed up all the rivers there are. Not much more there. Oh, we've got solar and we've got wind. We've got wind towers all over out here, but you got to be able to store it. Sometime the wind don't blow and the sun don't shine. Nuclear power is clean, effective, reliable. It works all the time. Medicine, the fear of radiation is causing a lot of people not to get a proper diagnosis of the diseases that they have. A proper diagnosis is essential for the cure, and radiation is used to cure a lot of cancers. I'm an old man, okay? Prostate cancer, radiated it, fine. I'm still here. Next slide. So, is Canada carry the scientific load? I was able to work with these guys and get some very, very nice papers out on low dose radiation. I really appreciated the opportunity that I had to do that. Next slide. So here's my summary. I can't see into the future. You can't see into the future. But I have a number of thoughts we can go on, hopefully building from the mistakes that we made in the low dose program. And these are some of the thoughts that I have. We need to have well-defined goals and questions that impact standards. When we were doing low dose, we just had all of this, like herding cats. We had people doing all this really good research, but it wasn't focused properly. We need to have an overview committee that helps us focus. We need to develop funding mechanisms that make it possible to do long-term research. You know, when I was a young man doing science, we had money. We did not have to spend our time chasing money. We had time to do research. That's what I did for a living. I did research. Now, if you want to get some funding and do some research, you better spend about 80% of your time chasing money. We need to have oversight that provides the changes in the new observation as the data is generated. Okay. We did not have that in the low dose program. We started off with it, but then with funding, decided we would do away with all of the outreach and communication, which is the next most important thing, I think, is to communicate the information that we get, both to those who make decisions as well as the public. We tried very hard to communicate and found it almost impossible. In fact, we even had a meeting with a bunch of the newspaper people in the Washington, D.C. area. We brought in all of our best sons. We had them talk to the newspaper people, showed them all this wonderful stuff. I can't get that into my newspaper. You're suggesting radiation is not as hazardous as we thought it was. Now, if you told me we found something new, front page, this type of stuff, my editor might stick it in the back, but nobody's going to see it. Communication is important and essential in any research that goes on now. So we need Canada and all the science around the world to continue to conduct high-quality research designed to inform decision-making in setting standards. Thank you. That's the end. We have time for questions if you have some.
Thank you, Dr. Brooks. Just a reminder to everyone attending, there is a speech bubble with a question mark at the top of your screen, and you are welcome to insert questions there. So Dr. Brooks, the first question is, how often should radiation safety standards be updated?
Well, you know, radiation safety standards are continually being evaluated. What really happens is that the NCRP and the ICRP, the National Council and the International one, make recommendations. Those are then given to the regulators, the EPA and the Nuclear Regulatory Commission, and they decide what the standards should be. And this is a continuous process, and I think it needs to be updated very regularly. We're still using some regulations that were written a long time ago. So that's a very good question, and I think it's essential that we continually incorporate the new science into the regulations. Very difficult thing to do. We tried that. We brought all the regulators, the DOE people, the scientists, got them all together in a room. The scientists presented, the regulators, the DOE people both slept. The DOE people presented, the scientists, the regulators slept. The regulators presented, everybody slept. My boss said that was a waste. No, that was a start. That's exactly what we need to do. We need to get these people together so they talk the same language, so the regulators can understand where the science is taking us. Thank you.
Thank you, Dr. Brooks. We have another question here. What range of doses are considered as low doses?
Well, you know what we did in the low dose program was says 10 rads or 0.1 gray was low dose. Now, a lot of times what we say is that a low dose is what is in the natural background range. Okay, if you live in Denver, Colorado, Albuquerque, New Mexico, or Salt Lake City, Utah, you're almost a mile high. Your dose is more than twice as high as people on the sea level. So that is a low dose, anywhere in that range. Now, there are some places in the world where the doses are very much higher than that. But a low dose we defined in our studies as 0.1 gray. Now, 5 rads or 0.05 gray is used as in the standards for exposures to nuclear workers. So that's a low dose. But low dose depends on who you are. Now, if you're an oncologist, you're radiating people, 2 gray is a low dose. 2 gray a day, every day, 5 days a week for 9 weeks, that was a low dose. 90 gray total, that's not low. But the individual doses of 2 gray were considered low. But for regulations, I think down where we're currently regulating and they're below there.
Okay, so another question, a bit of context here too. Science communication is not impossible. You need the proper training. You need social science experts to help you communicate these findings. Have you collaborated with non-radiation science engineering experts?
You know, when we first set up the low dose program, we had 5 groups that were exactly that. And their job was to communicate. Okay? And that was a nice balance. But as the funding started to get more competitive, oh no, we cut off everybody but me. And I was the communicator. A big mistake. I think exactly what the person is asking is for is essential. We have to have people outside the radiation field to help with the communication and help with the outreach and help understand where these people are coming from. Fear is very different, okay? I can be afraid of a snake. I don't care if it's a little garter snake or rattlesnake. If I see a snake, whoo, I'm afraid. A lot of people view that with radiation. They don't care if it's a lot or a little radiation. So all of these other areas that have a lot to contribute need to be included in any research plan now. Thank you. That's a good question.
So another question, are there any plans or discussions for the revival of the U.S. DOE low dose program?
Yes, indeed. They've actually put some money into a new program, and they've been having meetings to try to decide what to do with it. Now, what I worry about is that they're going to have enough meetings that they'll burn all the money just having meetings and not get any to the scientists. What you need to do is make sure the scientists are getting the money so they can get new information. But yes, we're very hopeful. I hope some of the money gets to where it needs to be, and that's the scientists.
Okay, so we have more questions coming here. Can you comment on the Japanese proposal to drain tritiated water, Fukushima, into the Pacific Ocean over some 25 years?
Yeah, see now, tritium is a very interesting radionuclide. It's a very, very weak beta emitter. It takes a lot of disintegrations from tritium to get a gray of radiation or a milligray of radiation. I remember going to Canada one time when Canadians were going to try to change the standards for tritium. Okay, now tritium, if you look at the standards across the world, wide range of standards, some very restrictive, some very, very lenient. So tritium is a very interesting isotope. It moves quickly through the environment. It does get into people. But the dose per disintegration is so low that you have to have a lot of disintegrations to get any dose. When I was at the meeting in Canada, I remember they were going to revise it down a long ways. We were in a room that's, you know, like a theater setting with higher and higher and higher. I calculated that the people sitting on the top row of that meeting, if they sat there for a month, would get about the same dose as someone would get from the tritium that they were proposing if they drank a liter of water every day for a year. So we can see that you're regulating way, 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 way back into the background, which is not necessary. We can detect it, we can measure it, but we don't need to regulate when you get down into very, very low levels. So what they're doing in the ocean's big. It dilutes very quickly. Sort of like the Columbia River here, big river, a little bit in there. We can still detect it, but it's so dilute that there's no biological effects. Red Karsten at Brookhaven had a bunch of mice that he fed tritium their whole life. I went back there and we did some chromosome studies, mutation studies, bunch of studies on those mice. Whew, it took a bunch of tritium to see anything. And they're regulating way, 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 way down into the background. So the disposal or discharge of tritium into the ocean is not a health problem.
Okay, I think we have time for one more question here. Despite so much data opposing LNT, why are we still not able to abolish it?
You know, that is a tough question and a good one, because we have lots and lots of data. We have it at all levels of biological organization. But you know, I think the fear is probably one of the reasons. Like I say, a person might be afraid of a snake, regardless what kind it is. They might be afraid of this or afraid of that. We have established the fear of radiation in our population, and the regulators, they have to write the regulations as best they can. And I've worked with NCRP, I've worked with the EPA, I was on the Science Advisory Board of EPA when we reviewed the Beer 7 report, okay? And my suggestion was the model that you're using, the LMT, is the biggest problem we have in regulations. They said, okay, Brooks, you go over and write a little sub-report and we'll put that in, but it never shows up. See, and so the regulations are tried to be very protective. They try to be, but what we have to show is that while protecting from radiation, you're maybe causing a lot of other things way, 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 way worse than the radiation you're protecting against. Now, we have built up this set of radiation protection standards over many, many years. And we're trying very hard to protect the public from anything that's going to cause any damage. So it's just very, very difficult to get those changed. I think, personally, that I've seen some shifts. I've seen some roles. I've seen a little recognition. In Beer 7, they recognize each one of those things that I talked about. Adaptive response, genomic instability. And they wrote about each one of them and says, well, these are nice observations, but we do not know enough about the mechanisms to use them yet in regulations. So I read the Beer 7 report and say, we need a little more mechanistic information. And about that time is when the DOE low-dose program was killed. Hopefully between the rest of the world and the new low-dose program, we can fill enough of that in that the regulators can say, yes, yes, we can change regulations. So far, that hasn't happened.
Thank you again, Dr. Brooks, for your time today. I will let you know there were some more questions that came in, and hopefully we can work with you on some responses, as we did record today's webinar, and everyone can stay tuned to receive a recording had you registered, and we'll also make it available via CNL's social media. And before we sign off, if I can just call on Dr. Azam, perhaps Dr. Azam, you can give us just a brief expectation for the future of CNL's low dose radiation webinar series.
Certainly. Thank you, Alison, and thank you very much, Tony, for a wonderful, wonderful lecture today, and we look forward to more dialogue on the effects of low-dose radiation. We will be holding our webinar series monthly. We may miss some months when we have holidays and so on, but looking forward to meeting everyone next month. Thank you, and thanks again, Tony, for giving us your precious time today. Thank you, and thanks everyone for participating in today's webinar. Thank you.
Thank you for letting me do it.